Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen that how to do a circuit analysis using the Laplace transform. And we have seen that this Laplace transform is a useful tool for the circuit analysis, specifically when we want to do a transient analysis of the circuit. Now in the previous video, the couple of examples that we have taken, in those examples, the initial conditions of the circuit were 0. But in this video, we will take few examples where we do have some initial conditions. And for such case, let us see how to do a transient analysis using the Laplace transform. So this is our first example. So in this example, we have been given this circuit and we have been given that the switch is in the position 1 since a long time and suddenly it changes to the position 2 at time t is equal to 0. So here we have been asked to find the capacitor voltage Vc of t for t greater than 0. So first of all, let us find the initial condition of the circuit. And for that, let us see the circuit at time t is equal to 0 minus. So at time t is equal to 0 minus, the switch will be at the position 1. And in the example, we have been given that the switch is in this position since a long time. That means in this position, the circuit is already in the steady state condition. And we know that in the steady state condition, the capacitor will act as a open circuit. That means at time t is equal to 0 minus, if we see the voltage across the capacitor, then that is same as the voltage across this 2 ohm resistor. So using the voltage divider rule, we can say that the voltage across this 2 ohm resistor or the initial voltage across the capacitor, that is Vc0 minus, is equal to this 2 divided by this 2 ohm plus 3 ohm times 10 volt, or that is equal to 4 volt. So we can say that the initial voltage across the capacitor or this Vc0 minus is equal to 4 volt. So now let us see the circuit at time t is equal to 0 plus. So now at time t is equal to 0 plus, the switch will be at the position 2. And as we have seen, the initial voltage across the capacitor will be equal to 4 volt. And now, since this part of the circuit is no longer in a use, so we can say that effectively this is the circuit at time t is equal to 0 plus. So now to find the voltage across the capacitor, first of all let us find the equivalent circuit in the S domain. So we know that if there is some initial voltage across the capacitor, then this is the equivalent S domain circuit for the capacitor. So here this C is equal to 0.1 Faraday. That means here this 1 over Cs will be equal to 10 divided by S. And we have seen that the initial voltage across the capacitor or this Vc of 0 is equal to 4 volt. So we can say that this voltage will be equal to 4 divided by S. And in the equivalent S domain circuit, the resistor will remain as it is. Now for this 5 ampere current source, the equivalent S domain representation will be equal to 5 divided by S. That means if we see the overall S domain circuit for the given circuit, then this is how it can be represented. And as you can see, this Vc of S is the voltage across these two elements. So now to find this Vc of S, let us apply the KVL in this loop. So let's say the current in these two loops are I1s and the I2s respectively. And here, while applying the KVL, just for our convenience, instead of this current I1s and the I2s, simply we will write only I1 and I2. That means if we apply the KVL in the first loop, then we can write it as this 4 times I1, that is the voltage drop across this 4 ohm resistor, plus 10 divided by S times I1, that is the drop across this capacitor, plus 4 divided by S, that is the drop across this voltage source, plus 2 times this I1 minus I2, that is equal to 0. Or further if we simplify it, then we can say that that is equal to this I1 times this 6 plus this 10 divided by S, that is equal to minus 4 by S plus 2 times I2. And as you can see over here, this current I2 is same as the 5 divided by S. So we can say that this I2 is equal to this 5 divided by S. So if we put the value of current I2 in this expression, then further we can write it as this I1 times 6 plus 10 divided by s, that is equal to minus 4 by s plus 2 times 5 by s, or that is equal to 6 divided by s. That means we can say that this current I1 is equal to 6 divided by s divided by 6 plus this 10 divided by s. So in this way, we got the expression of the current I1. Now if you see over here, then this voltage Vc of s is the voltage drop across these two elements, and that is equal to this 10 divided by s times I1 plus 4 by s. So now in this expression, let us put the value of current I1. So in this expression, if we put the value of current I1, then we can write it as this 10 divided by s times this 6 divided by s divided by 6 plus this 10 divided by s plus 4 divided by s. So if we further simplify it, then we can write it as 60 divided by this s times this 6s plus 10, and over here we will also have this 4 divided by s. So now in this expression, if we take this 6 outside, then further we can write it as this 10 divided by s times s plus 10 divided by 6 plus 4 divided by s. So now for this first term, let us use the partial fraction expansion and let us simplify it. So if we use the partial fraction expansion, then we can write the first term as this a divided by s plus b divided by this s plus 10 divided by 6. And here the third term will be equal to 4 divided by s. So now using the residue method, we can easily find the coefficients a and the b. That means for finding this coefficient a, what we will do? We will multiply this first term by the s, and we will evaluate the value of this expression at s is equal to 0. So now this s in the numerator and the denominator will get cancelled out. And now in this expression, if we put the value of s is equal to 0, then the value of a will come out as 6. Similarly, for finding this coefficient b, we will multiply this term by this s plus 10 divided by 6, and we will evaluate the value of this expression at s is equal to minus 10 divided by 6. So now as you can see, this s plus 10 divided by 6 in the numerator and the denominator will get cancelled out. And now if we put this value of s in the given expression, then the value of b will come out as minus 6. So in this way, we got the value of a and the b. So after putting the value of a and b, the expression of the Vc of s can be written like this. And further, if we add these two terms, then we can write this expression like this. So now as you can see, we can easily find the inverse Laplace transform of the given expression. So we know that the inverse Laplace transform of the 1 divided by s is equal to u of t. And using the frequency shifting property of the Laplace transform, we can say that the inverse Laplace transform of the second term is equal to e to the power minus 10 divided by 6 times t times u of t. And along with the coefficient, this is the expression of the Vc of t. So now, if we take this u of t outside, then further it can be written like this. That means this is the expression for the voltage across the capacitor. So in this way, with the help of the Laplace transform, we can easily solve the examples based on the transient analysis. Now if you closely observe, then the given circuit is the first order circuit. And for the first order circuits, if you want to find the transient response, then we can even use the conventional method. But from the first order circuit, as we go towards the second order circuit, like the second order RLC circuits, then it is difficult to solve using the conventional method. And for such second order circuits, it is always useful to solve it using the Laplace transform. So now, let us take a couple of examples based on the transient analysis of the second order circuits. And let us see how we can solve such circuits using the Laplace transform. So in this example, we have been given this circuit, and here we have been asked to find the current through the inductor for the time t greater than 0. So here we have been given that initially minus 1 ampere current is flowing through the inductor, and the voltage across the capacitor is equal to plus 5 volt. That means here we have been already given the initial conditions. So here for finding the current through the inductor, First of all, let us draw the equivalent S-domain circuit for the given circuit. So we know that whenever there is an initial current through the inductor, then in the S-domain, this is how it can be represented. So here, since L is equal to 5 Henry, so this Ls will be equal to 5S. Similarly, we know that if there is an initial voltage across the capacitor, then in the equivalent S domain, this is how it can be represented. So here, for the given circuit, this first representation of the capacitor will be more useful. And therefore, while solving the circuit, we will use the first representation. So as you can see over here, this C is equal to 0.1 Faraday. That means here, this 1 over Cs will be equal to 10 divided by S. Similarly, for the resistor, if we see, then in the equivalent S domain, it will remain as it is. That is equal to 10 divided by 3. And if we see this voltage source, then it is the unit step function. So in the equivalent S domain, that is equal to 10 divided by S. So now, if we see the equivalent circuit in the S domain, then this is how it can be represented. So here, we have been given that the value of this initial current through the inductor is equal to minus 1 ampere. So we can say that this current source is equal to minus 1 divided by S. So simply, we can write it as 1 divided by S, and we can reverse the direction of the current source. Similarly over here, the initial voltage across the capacitor is equal to 5 volt. That means this current source will be equal to 5 divided by 10, or that is equal to 0.5 ampere. So with this modification, if we see the equivalent circuit, then this is how it will look like. So here, the current in this branch will be the current through the inductor, and the voltage at this node will be the equivalent voltage across the capacitor. And as you can see, the same voltage will also appear across the inductor. So here, to find the current through the inductor, first of all we need to find this Vc of S. And to find that, let us apply the KCL at this node. So applying the KCL at this node, we can write it as this Vc minus 10 divided by S divided by 10 divided by 3, that is this current, plus Vc divided by 5S, that is this current, minus 1 divided by S, that is this current, plus Vc divided by 10 divided by S, that is this current, minus 0.5 ampere, that is this current, and that is equal to 0. So further we can write it as this 3 times Vc divided by 10 plus Vc divided by 5S plus S divided by 10 times Vc minus 10 divided by S divided by 10 divided by 3 minus 1 divided by S minus 0.5, that is equal to 0. Or further we can write it as this Vc times this 3 divided by 10 plus 1 divided by 5S plus S divided by 10, that is equal to this 3 divided by S, that is this term, plus 1 divided by S plus 0.5. So here, if we combine these two terms, then that is equal to 4 divided by S. That means on the right hand side, we will have this 4 divided by S plus 0.5. So now, if we multiply both sides by the 10s, then we can write it as this Vc times these 3s plus 2 plus s square, and on the right hand side we will have these 5s plus 40. So we can say that this Vc is equal to these 5s plus 40 divided by s square plus 3s plus 2. So in this way we got the expression of the Vc of S. And as you can see over here, this current IL of S is the current through these two branches. So we can say that this current IL of S is equal to Vc divided by 5S, that is this current, minus 1 divided by S. And we have seen that this Vc is equal to this 5S plus 40 divided by S square plus 3S plus 2. So in the denominator of that, we will have this 5S. And over here, we will have this minus 1 divided by S. So further we can write it as this 5 times this S plus 8, and in the denominator we will have this 5 times S square plus 3S plus 2. And over here, we will also have this minus 1 divided by s. That means further we can write it as this s plus 8 divided by s times this s plus 2 times s plus 1. And over here, we will also have this minus 1 divided by s. So this will be the expression of the current IL of s. So in this way, we got the s domain expression for the IL of s. So here, using the partial fraction expansion, further we can simplify this part. So for the first part, if we do the partial fraction expansion, then we can write it as a divided by s plus b divided by s plus 1 plus c divided by s plus 2. And now, using the residue method, we can easily find the coefficients a, b and the c. So now, for finding the coefficient a, what we will do? We will multiply the left hand side by the s, and we will evaluate the value of the expression at s is equal to 0. So now as you can see, the s in the numerator and the denominator will get cancelled out. And in this expression, if we put the value of s is equal to 0, then the value of a will come out as 4. Similarly, for finding the coefficient b, we will multiply the left hand side by the s plus 1, and we will evaluate the value of the expression at s is equal to minus 1. So now, these two terms will get cancelled out, and in this expression, if we put the value of s is equal to minus 1, then the value of b will come out as minus 7. Similarly, we can also find the coefficient c. So for finding the coefficient c, what we will do? We will multiply the left hand side by the s plus 2, and we will evaluate the value of the expression at s is equal to minus 2. So once again, this s plus 2 in the numerator and the denominator will get cancelled out. And now, in this expression, if we put the value of s is equal to minus 2, then we will get this 6 divided by this minus 2 times minus 1, or that is equal to 3. That means the value of the coefficient c is equal to 3. So in this way, we got the value of the coefficients a, b and the c. So after putting the value of a, b and the c, the expression of the current IL of s can be written like this. So as you can see, here we have also added the last term. So if we combine the first and the last term, then this expression can be written like this. And now as you can see, we can easily find the inverse Laplace transform of the each term. So we know that the inverse Laplace transform of this 1 divided by s is equal to u of t. And using the frequency shifting property, we can also find the inverse Laplace transform of the second and the third term. That is e to the power minus t times u of t and the e to the power minus 2t times u of t. And along with the coefficients, this is the expression of the inductor current. So as you can see, when we are dealing with the second order RLC circuits, then with the help of the Laplace transform, we can easily do the transient analysis. So similarly, let us take a couple of more examples. So in this example, we have been given this circuit, and we have been given that the switch K is in the closed condition before the time t is equal to 0. That means initially, there is a no charge across the capacitor, or there is a no current through the inductor. And at time t is equal to 0, this switch has been opened. So here, we have been asked to find the voltage V of t across this parallel circuit. So here, since the switch is opened at time t is equal to 0, so this current source will get applied to the circuit at time t is equal to 0. That means at time t is equal to 0 plus, this is how the circuit will look like. So here, to find the expression of this V of t, first of all let us represent this circuit in the S domain. So here, we have been already given that the initial condition of the circuit is 0. That means there is a no initial charge across the capacitor, or there is a no initial current through the inductor. So in the equivalent S domain, this capacitor can be represented as this 1 divided by Cs. And here, the value of C is equal to 1 farad. That means this is equivalent to 1 divided by S. Similarly, the equivalent representation of the inductor in the S domain is equal to Ls. And here, the value of the L is equal to 0.5 Henry. So we can say that is equal to 0.5 S. And for the resistor, it will remain as it is. That is equal to 0.5 ohm. And if we represent this current source in the S domain, then that is equal to 2 divided by S. And let's say the equivalent voltage in the S domain is equal to V of S. That means for the given circuit, if we see the equivalent circuit in the S domain, then this is how it will look like. So now, by applying the KCL, we can easily find this voltage V of S. So to find that, let us apply the KCL at this node. So applying the KCL, we can write it as this V divided by 0.5 ohm, that is this current, plus V divided by 0.5 S, that is the current through this branch, plus V divided by 1 divided by S, that is current through this branch, that is equal to 2 divided by S, that is the incoming current. Because as you know, as per the KCL, the summation of the incoming currents should be same as the outgoing currents. So further we can write it as this V times this 2 plus 2 divided by S plus S, and on this side we will have this 2 divided by S. So now if we multiply both sides by the S, then we can write it as V times 2S plus 2 plus S square, and over here we will have only 2. That means this voltage V is equal to 2 divided by this S square plus 2S plus 2. And further we can write it as this 2 divided by this S square plus 2S plus 1 plus 1. Now we know that this term is equal to S plus 1 whole square. So we can say that this V is equal to this 2 divided by this S plus 1 whole square plus 1 square. Now we know that the Laplace transform of the sine omega t is equal to omega divided by this S square plus omega square. That means over here this omega is equal to 1. And now using the frequency shifting property of the Laplace transform, we can say that this V of t is equal to 2 times this e to the power minus t times sine of t. Because we know that the Laplace transform of the term e to the power minus at times sine omega t is equal to omega divided by this s plus a whole square plus omega square. So over here this a is equal to 1. So we can say that this V of t is equal to 2 times this e to the power minus t times sine of t. So in this way we got the expression of this voltage V of t. So similarly, now let us take the last example. So in this question, we have been given this RLC circuit, and in this circuit, this switch K is closed at time t is equal to 0. So in the question, we have been given that initially, this capacitor is charged to some voltage V0, and here we have been also shown the polarity of the initial voltage. So here, we have been asked to find the current through the given circuit for the time t greater than 0. So in the given circuit, at time t is equal to 0, this switch has been closed. That means if we see the circuit at time t is equal to 0 plus, then this is how it will look like. So now, to find this current I of t, first of all let us find the equivalent S-domain representation for the given circuit. So we know that whenever there is some initial charge across the capacitor, then in the equivalent S-domain, this is how it can be represented. That is 1 divided by Cs in series with this V0 divided by S, where the V0 is the initial voltage across the capacitor. So here, the value of the capacitor is equal to 0.5 Faraday. That means this 1 over Cs will be equal to 2 divided by S. And here, the initial voltage across the capacitor is equal to 1 volt. That means this term will be equal to 1 divided by S. So that is the equivalent representation for the capacitor. Similarly, for the inductor we know that the equivalent S-domain representation is equal to Ls. And here, since the L is equal to 1 Henry, so that corresponds to S. And for the resistor, we know that the equivalent S-domain representation will remain same. That means this 2 ohm will remain as it is. So in this way, we got the equivalent S-domain representation for the each element. And now, if we see the equivalent circuit in the S-domain, then this is how it will look like. So now, to find this current I of S, let us apply the KVL in this loop. So applying the KVL, we can write this 2 times I, that is the voltage drop across this 2 ohm resistor, plus S times I, that is the voltage drop across this inductor, minus 1 divided by S, that is the voltage drop across this voltage source, plus 2 divided by S times I, that is the voltage drop across this capacitor, and that is equal to 0. So further we can write it as I times this 2 plus S plus 2 divided by S, and that is equal to this 1 divided by S. And now if we multiply both sides by the S, then further we can write it as I times these 2S plus S square plus 2, and on the right hand side we will have only this 1. That means this current I is equal to 1 divided by this S square plus 2S plus 1. And like we have seen in the previous example, further it can be written as 1 divided by this S square plus 2S plus 1 plus 1. So we know that this term is equal to S plus 1 whole square. So we can say that this current I of S is equal to 1 divided by this S plus 1 whole square plus 1. So we know that the Laplace transform of the e to the power minus at times sin omega t is equal to omega divided by S plus a whole square plus omega square. That means over here the value of the omega is equal to 1. So if we take the inverse Laplace transform of this term, then we will get this e to the power minus t times sin of t. So we can say that the current through the given circuit, or this I of t, is equal to e to the power minus t times sin t. So in this way, with the help of the Laplace transform, we can easily find the transient response of the second order RLC circuits. So I hope through these examples you understood how we can use the Laplace transform for the circuit analysis and how we can find the transient response of any circuit. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.